being there. Huh? All right. Good start. All right. Good morning, everybody. Good morning, Mr. Samuelis. Yeah. All right. So moving on, we got some people that got to make up the quiz. So we won't look at those yet. We don't have much more for this chapter. I think I only have a couple days of 6-3, and then review and possibly a test. So hopefully look forward to that. So the next thing, what we've done so far is Euler paths and Euler circuits, and now it's time for Hamiltonian. Can everyone say Hamiltonian? Did you hear him? Wow. All right. So Hamiltonian path is something actually completely different, not related to an Euler circuit or path at all. Okay. So Hamiltonian path. Remember, a path is just jumping from one vertex to the next. Nothing special. You can't use edges twice. But a Hamiltonian path is a path that visits each vertex exactly once. And then we're going to talk about the Hamiltonian circuit. Hamiltonian circuit, you know what a circuit is. You end where you started. So you do everything that you needed to do in that previous thing, but then end where you started. Now, I want you to put this down for this particular when would we need this. And this is the classic UPS driver. What a UPS driver has to do is leave base, has to go to all the houses, and then end up back at the base. Do you want to go to a house twice, or you only need to visit once? In a particular day, you only need to visit once. So that's what the vertices represent, the houses that you're visiting. There's no point in going to something twice. So that is why this would be an application for this. And then jumping ahead, we do have a project at the end of this after taking the chapter test, where that's exactly what you're going to do. You're going to leave your house, and you're going to pick, I think it was 5 colleges that you might want to go to. You're going to investigate all the mileages to the from house to college, and actually from college to college. And that's just a Google Maps thing. It just takes a little bit of time. And then you're going to do what we're going to do today as far as trying to find the best possible way to get from your house to all the colleges and back. And of course, the best possible way would be the shortest possible way. We'll talk about that, how challenging that can be. So we'll just take it from there. Okay, so looking at this first one, I did forget to grab something, but we'll try to make this happen. Let's do a Hamiltonian path first. And again, this was part of your job for your test, like writing out the vertices. So I'll write this down first. Hamiltonian, I'm just going to put ham path, which means I don't have to end where I started. And I don't know if there's going to be hard, fast rules for this. You just have to, avoid hitting a vertex twice. Okay, let's just put it in those terms. Okay, so we'll start with A. All right, so if I go this way, A to G, okay, I've already visited G. Not that I even have a chance of visiting it a different way in this particular situation. Then, obviously, I can only go from G to F if I decided to go this way. So G to F. Now F is visited. Even if I had another way of getting to F, I will not use it. Okay, F is done. We've delivered the package. We will never go back to F. I want you to think about that when you're thinking about Hamiltonian. Then F to E is a possibility. Now we got some possibilities, what I was going to say next. You either go E to C or E to D. All right, that's one of my two choices. I'm just randomly going to go E to C. Okay. Meant to do that green. This is so hard in this program to switch back and forth. Then, of course, I could go C to B and then B to D, and that would be a legal Hamiltonian path. But if I choose that, can I now make this a circuit? Yes or no? Okay, so I can write then B, then D. This is a Hamiltonian path, but what I've done is shut down my possibility of making a circuit. So it's a path, and it's Hamiltonian. Every vertex was visited because I started with A. Just my choice there makes me not able to make a circuit out of it when I'm done. So what I'm going to do is now talk about a Hamiltonian path, or circuit, sorry. Ham circuit. And make a little different decision at the end there. I'm going to, well, maybe I'll just go in green. A to G, G to F, F to E, E to C, and then for me to really be able to make this a circuit, I have to go, what in the blazes just happened there? Oh my goodness. Then C to D, then D to B, then B to A, and that's a Hamiltonian circuit. Was every edge used, by the way, yes or no? No, and that's not what has to happen with a Hamiltonian situation. You just have to hit every vertex once. To make it a circuit, then I must end up where I started as well. E, then C, then D, then B, and then I end up back at A. All right? So, Hamiltonian path, you don't have to end where you started. Hamiltonian circuit, you hopefully see the difference. Okay? Alrighty then. Okay, so this previous graph, as you were writing, hopefully the stuff down when you were leaving, is not a complete graph. Okay, and that's probably what we're going to be dealing with the rest of the way. Your college project, you will make a complete graph, meaning you pick 5 colleges, you will have to find all the distances from your home to all the colleges, but then all the distances from the colleges to the colleges, every single one of them. Okay, and then that makes it a complete graph. You have all the distances of all the different vertices all written down. So I do like referencing this so you have an idea what the future holds, the kind of thing I'm going to have you do, and we'll give you time to do that. So, complete graph in which every pair of vertices is connected by exactly one edge. You know that there are times that we had, we were dealing with Euler, there were 2 paths to vertices, and sometimes that's needed probably in electrical situations or something like that. But we're only going to talk about one connection between every vertice, and every vertice is connected to every other vertice. Okay, that is what a complete graph is. Okay, so again, n is the number of vertices. In this particular case, I guess I'll pick a different color here. We have 5 vertices, right? A, B, C, D, E. And the number of edges will always be in a complete graph the following. N times n minus 1 divided by 2. Okay, so this you can call, and I wrote this in blue so you can really identify this, a formula. I think it's the second one that we have to have memorized for the upcoming test. We'll talk about the other one. I forgot, but I'm just thinking about another formula I threw down in previous notes. It's leaving my mind for a second here. So in this case, we could actually count these, but just want to make sure. We have 5 vertices. N minus 1 is 4, so that's just the number thrown in, divided by 2. That equals 20 divided by 2, which is 10. If you count the amount of edges that are in this graph, there are 10 of them. Okay, so that's just what that is. Now, this is where this gets crazy. And I don't know if we had a chance to watch this, but the movie I showed, Algorithms, anyone remember that from first semester? We showed 2 things. Prediction by the numbers for statistics, then an algorithms show. And it was stated as the traveling salesman problem, where this gets crazy. And what we're going to do next is actually really hard for people to figure out the best possible way to get from one vertex to another one and back, creating the best Hamiltonian circuit you can. And I think I'm going to show that again within the next couple of days, at least that little excerpt. And there was a B in it. Anyone did that? Maybe I didn't get to that part, first hour. So we'll show that again. So it sounds like I'm kind of blabbering here, but I just wanted to share that with you, that that's the possibility. And then here's the next thing. All right, if I have n vertices, then the possible number of Hamiltonian circuits is 5 factorial. So I can come up with 5 factorial different Hamiltonian circuits when I have 5 vertices. Of course, 5 factorial is 5 times 4 times 3 times 2 times 1. And I think that's 20, 3 times 20, 60. That's 120 different Hamiltonian circuits, unique ones, that I could create out of this situation. Okay? And then that's where the problem comes in. UPS driver probably has, I don't know, I don't want to throw out something crazy there, but maybe 150 different vertices. Meaning they start here, then they have to go to 149 homes and then come back. That's 149 factorial different Hamiltonian paths. And then when you come back home, that makes it a circuit that could be calculated to find out the best possible way. And of course, UPS cares about that. They try to shave every penny possible to optimize, the money they make. So they don't want to be doing the longest path to get back home. They want to shorten it as best as possible. So this is where this gets a little crazy. So, all right, so to find a Hamiltonian path, you can actually basically list any of the vertices. It doesn't really matter, how you do this. But let's start with A. Starting from A, I could go to any vertex. And, of course, probably the first thing you'd probably do is this. A to B, B to C, C to D, and then D to E. That's a Hamiltonian path. You just hit every single vertex. Then to make it a circuit, you just come back home. So there's one. Go back. I could start at 8. Why would that do that? Back button. Okay, back. Oh, you dirty little. All right, back. Okay, there we go. Here's a different one. I could start at A. I could go to B. But then I could go to D. And then to C. Then to E. Then to A. Okay, before I went back to A, it was a path. Now it's a circuit. I visited every single vertex once. That is a different Hamiltonian path using A as your starting vertex. Or, one more, I could start at A and I could go to E. Then I could go to B. Then I could go to C. Then to D. And then back to A. So I just showed 3 different Hamiltonian paths, then turned it into a circuit when I came back home. That's just from starting from A. We could have started from E, and that's said to be a different Hamiltonian circuit because you started somewhere different. And that's the idea behind this. That's what it means about different Hamiltonian paths or circuits. Depending where you start and what vertices you use next, that's why there's so many possibilities. And I could have listed those, but I didn't, for time's sake. All right? Okay, hit a pause for a second. Now, something that was blabbering about has to do with this third and last thing that we're going to do, but it is going to take a while. I almost feel like doing it on the board as well, but because of the movie, I'll do it on this screen here, and then show you how this actually works. Okay, so the whole idea of a UPS driver, and of course, yes, they have computers that actually probably do this work, but you got to know how to program a computer so people have knowledge of this Hamiltonian idea in order to make these programs happen. So what we want to find is if the UPS driver has to start at A and end at A, and all those other things represent houses, what is the shortest distance to get from A, hit all the vertices, all the houses, and come back to A? Shorter distance means less gas money, means less time, usually, depending on the paths and the kind of roads that they are. So here's one way we could do this. And this is the way that we're going to cover today. Tomorrow we'll share another way. It's called the nearest neighbor algorithm, the repetitive nearest neighbor algorithm. It's a series of tests. And then after you do these tests, you figure out which one's the best, and then you move on. Okay, and it is an approximate least cost Hamiltonian circuit because this is not a perfect process. When I show you the video, maybe we could start that tomorrow, show you that video about that little part about this, what's called the traveling salesman problem. It's a really tough thing to do. It's actually a mathematical conundrum right now to come up with the best possible way to do this. So this is just one way that we can kind of do okay in finding out that best way for the truck. But yeah. So what we have to do for, and I should put this down, I think I have it later, for the amount of vertices you have, that's how many tests you have to do. Now I'm not going to get any bigger than 6. I think our college project is we have 1 house and 5 colleges. Okay, so you have 6 vertices. The repetitive nearest neighbor algorithm, you will do 6 different Hamiltonian circuits and get their weights. Okay, so 6 vertices, you have to do 6 tests. For each test, you pick a starting vertex. That's where the 6 tests come from. The starting vertex is different for each test. If we have A, B, C, D, E, and F, I will start with A in the first test and end at A. Then the second test is start at B, end at B. Third test, C, end at C, so on and so on and so forth. So that's number 1. I don't really have that written until the end. You can make a note to self. So we pick a starting vertex, check all the edges, all of them that are unused, and select the lowest weights. No matter what vertex that goes to, that is the edge you're taking. Then from the next vertex, you do the same thing. Of course, you can't go back to the starting vertex until the end. So then you continue to look at the next lowest weight to connect a different vertex. Keep doing that until you come back home or come back to the beginning vertex. All right, so that's what step 2 is. So here's what I said here, and we do have that if you want to officially write this down. You do this process starting at each individual vertex. This means if you have 6 vertices, you will complete 6 different Hamiltonian circuits, each one starting from a different vertex. The one, and you're going to find out that sometimes you end up with the same looking picture, but the one or ones resulting in the lowest weight is your least cost Hamiltonian circuit that you can find from this process. Doesn't mean it's the best. Like I said, for 6 vertices, there's 6 factorial different possibilities, which is 6 times 120. 600, 6 times 20, so 720 different possibilities. And then once you get to 8 vertices, 9 vertices, it gets really impossible to write them all out. So this is just a process that may give you at least a good one, maybe not necessarily the best one. Okay, with all that being said, take a moment to write that picture down. And the weights, let's pretend it's a UPS driver, and we pretend the weights represent miles. All right? Pretend. So there are 5 vertices. This is what you should do. You know what? I'm gonna do this way and use my paper this way. Come on. Come on. Yes. No. Come on. Oh, for the love of dog, this program is the worst. Plus I'm shaking. I must have had too much coffee. Where's my there it is. Paste. That's great. Just great. That's where I wanted it. That's exactly where I wanted it. It's a stunning video. How many times am I going to cut and paste this? What did I say? How many tests were there? 5. So I want to cut and paste this 5 times. Oh, my word. Okay? 5 times. You okay over there? Okay, we'll do this offline. This computer program is the worst. I've been completely betrayed by this program, so we're going to move on. All right, so here's the first test. All right, stick with me. We're going to start with A. So I'm not going to write that down, but the first test is you start with A, and you do this little process. Looking at A, okay, so I can move in on this, and I'm just going to keep track of the numbers as we write. I could actually write it real tight with this. You pick the lowest edge coming from A, since I'm starting from A. Which one is that? 12, 11, 12, or 9? This is not rocket science, right? So 11, and I'm going to write that, and I'm going to write it tight to that. Now I'm at D. Okay, now, what you have to understand is I have to void A until the end. So now I'm at D. The remaining edges from D, which one is the smallest, and who does it go to? Okay, 6, and it goes to E. So I'm going to select that one. And that's a weight of 6. Now I'm at E. I can only go to B or C. I don't want to close off A yet. I end at A. So I don't want to, ruin that yet. That's the very last edge I have. So I can only go to B or C. Which one's smaller? B, which is a length of 14. Really isn't that hard once you look at what we're doing here. Now I only have one option. I cannot close off A. I started at A. I have to end at A. So I am forced to do C, which is 13, and then I must end up at A and be finished there, and that is 12. And I don't know why that didn't write. And then the only thing you have to do, boy, I'm going to have to do this mental math, is add these. Well, 6 and 4 is 20, 31, 41, 43, 53 is at 56, I believe. Okay, so think of that as 56 miles. All right, now we got to see, is that the smallest Hamiltonian circuit that we have here? We'll find out. Then the next thing you have to do is start at a different vertex. Now we'll start at B. And we'll do the nearest neighbor, picking the lowest I possibly can as I move along. All right, so again, we'll talk about this maybe tomorrow and clean this up, why this is not the perfect way, but at least it is way to try to get something pretty good out of this. What's the smallest segment coming from B? What's the smallest weight? 13 I'm stuck with. So I have to go 13, B to C. So again, looking at B, I have 13, 18, 14, and 19. So I'm selecting the smallest one. And then sometimes this results in the same looking picture. So do be aware of that. And I could have listed the vertices, and I should have. Let me go back to that one. I went A to D, then D to E, then I think I went E to B, B to C, and then C to A. I should have wrote that on that first one. Okay? Now the next one, B, 13. All right, what's the next smallest edge coming from C? And looking at this picture, of course, I can go to C, D, E, or A. Those are my next possibilities. Which one should I go to, D, E, or A? It's D, because that one's 7. Don't worry about the change of colors. I'm not going back and forth up there in this crazy program. Who should I go next? Should I go D to E or D to A? E, it's the smallest of the two edges. This is not rocket science, right? Okay, and what we're just trying to do is see what happens. And then E has to go to A because I can't close off B without going to A. We got to visit A's house, deliver the package, and then end up at B, which is 19 miles. Okay, much different graph, all right? And we'll get that weight here shortly. Yes, Mr. Samuelis. Okay, so what does that say about this one? Will we use it or not? This one's out because the first one was better than that one. It's 1 mile shorter. Okay, now what do we have to do? Keep going with the process. Fine, since the computer doesn't like me. I got to rewrite all these vertices. Okay, and then I could just keep track. And I should have wrote this down. I went B to C to D to E to A back to B. Right? And then the next one we're going to start with is C. We're going to start here. So that's all you have to do is start a different vertex and go through this process. And many times you will get the exact same looking graph. The only reason you can consider it being different is you started with a different vertex. But then we'll talk about that when we do our project. Okay, what should I do first with C? What edge? What number? What number should I do first, everybody? 7. Which goes to D. Then I think this one's going to be a repeat. Then what should I do next? From D, what's the next smallest one? 6, 11, or 18? 6. Think we're going to get a repeat here. 14 or 12. Which one should I do next? 14 or 12? 12. Tain't no rocket science. And then I'm stuck with going to B, which is 19. And then C, which is 13, which is exactly the one we just had here. We had a 57 for that one. This one will be out. But the reason this is different is you started at C. Okay, so this is just an algorithm to test, can I get a lower weight out of one of these traveling situations. All right, because I couldn't copy and paste, just real quick do this and keep track of your letters, and I'll just go through the process. Now it's D you start with. Highlight that in yellow. And then starting from D, let's see if we get anything unique here. Well, it doesn't look like it, because where do I first go to? Who's the lowest weight coming from D? Yet again, it's still 6, all right? Because we only have 5 vertices, we're not getting a lot of differences here. The more vertices, every test probably would be different. You know, and that's the idea behind this. All right, to E, and then coming from E, I actually have 3 possibilities, but it's still not great. We still have A that we have to pick because it's smaller. Okay, so that's 12. And now we finally get a little difference, okay? Because now I'm at A, and I can see that I'm at A, and I can only go to B or C. And in this case, C is a little bit better. So now that's what I'm going to choose to do there. C is 12 instead of 19. Okay? So, starting from D, had to do 6, had to do 12. Now we got one difference from all the other graphs. Okay, so maybe this may end up being all right, but we'll see. I have to go to B before I end up at D. And then going from there to there, that is 18. And I can put that right there instead of somewhere else. Okay? Now when I add that one up, we're definitely going to get a different sum. We should anyway, but 30, 43, 55. Ooh, that ended up being 61. Okay, that's real bad. So that one will be out because right now 56 is my winner. Then the last test is starting from E. All right. Again, this is an algorithm. It is far from perfect. When we finally get a winner out of these 5 tests, there may be an even better route here, but this is just an idea. Okay, so starting from E, the smallest weight actually is going backwards to D. So, and I forgot to write my vertices in that last one. We could go ahead and write that down as far as what that path was after I'm done with this one. And then D to C. Okay, so looking from D, kind of pointing on the screen here, 11, 18, or 7. You pick the smallest one. So you go back to 7. Again, sometimes these repeats. Same graphs. We'll see if that happens on this one. All right, and then coming from C, you can only go to A or B. All right, and it's going to be A in this case because it's just a little bit shorter there. Okay, so we're going to go to A, which is 12 again. And then we have to go to B. We have to select that 19. And then we have to end up there with that third. Oh, I made a mistake. That was a mistake. That was a brain misfire. We have to end up at E, which is 14. Okay, was that 14? I got that one right? All right, 14 right there. So this one is 19, 29, 31, 41, 45, 45, 52, 58. Okay, so after all that, our first test, was that right? Did I sum that up correctly? 6, 45, 51, yeah, 58. Actually, our first test ended up being the best one. And what you should do is actually show where you went. So E to D, D to C, C to, I think it went up to A, then A to B, and then B to E. So why these are all different is you started at different vertices. So from this algorithm, it only did 6. And not all of them are different. Actually, 2 of them ended up being the same subgraph. Okay, so we only did 6 out of 120 possibilities. Right, and that's what you need to understand. This is not perfect. All right, but it is a way to at least throw out some that are not so great, and so on and so forth. So that's all I got to do, and hopefully that makes sense. I guess is all I got to say about that.